Welcome to this explainer, where today we're taking a macro journey into one of organic chemistry's most fascinating magic tricks. If you've ever stared at a reaction pathway and wondered how a molecule essentially rewires its very skeleton, you are absolutely in the right place. Let's jump right in. Picture this. You start a chemical reaction with a very specific number of carbon atoms, right? But when you check your final product, boom, one of those carbons has completely vanished from your main chain. It hasn't just migrated somewhere else, it is totally gone. So how does a molecule surgically remove a piece of itself without falling completely apart? Well, today we're going to solve this molecular mystery by unpacking the Hofmann rearrangement.
To keep us from getting lost in the weeds, here is our roadmap for the explainer. We'll cover 1. The missing carbon transformation, 2. The 6-step mechanism, 3. The concerted 1-2 shift, 4. The primary amide rule, 5. Perfect stereochemical retention, and finally, 6. Real-world industrial applications. All right, Section 1. The missing carbon transformation, from amide to amine. At a really high level, the Hofmann rearrangement takes a primary amide, treats it with diatomic bromine and a strong aqueous base, usually something like sodium hydroxide, and yields a primary amine. But here is the crazy part. That primary amine is specifically 1 carbon shorter than your starting material. That missing carbon, it's ultimately kicked out as carbon dioxide gas. So you aren't just swapping functional groups here, you are actively shrinking the entire carbon skeleton. Section 2. The 6-step mechanism, zooming into the subatomic level. Now, if we break down the exact journey of these molecules, you'll see this is definitely not a simple one-step swap. It's a highly structured 6-step sequence. Step 1 is deprotonation. The strong base attacks the amide to form an anion. Step 2, that anion attacks the bromine to form an N-bromoamide. Okay, step 3, the base attacks again, ripping off a second proton to create a super unstable bromoamide anion. Step 4 is the grand rearrangement itself, the 1-2 shift. Step 5 brings water into the mix to form a carbamic acid. And finally, step 6, the carbamic acid breaks down, releasing carbon dioxide gas and leaving us with our shortened primary amine. Tracing this classical reaction pathway, you can literally follow that missing carbon right up to the very end. Notice the N-bromoamide intermediate there at Roman numeral 2 and that unstable anion at Roman numeral 3. Then, watch how the whole thing transforms into an isocyanate at step 4. Finally, water attacks to form that unstable carbamic acid intermediate, which just spontaneously falls apart to release CO2. It really shows how that specific carbon atom attached to the oxygen is just cleanly snipped right out of the chain. Section 3. The concerted 1-2 shift, the climax of the reaction. So that 1-2 shift we just mentioned, it is absolutely not some clunky step-by-step process. Research actually shows it's a concerted mechanism. That means the migrating carbon group breaks its bond with the carbonyl carbon at the exact same split second it forms a new bond with the nitrogen. And right at that same moment, the bromine atom takes its electrons and bails as a bromine ion. This brilliant synchronized dance creates a vital bridge called an isocyanate intermediate. The carbon in this isocyanate is double bonded to an oxygen and double bonded to a nitrogen, which makes it a massive, irresistible target for the water molecule that attacks it in the next step. Section 4. The primary amide rule. Why secondary amides failed the test.
Now, you might be wondering, can we just use any amide for this? Like, what if we throw a secondary amide in there? Well, because this mechanism specifically demands 2 deprotonation steps, one before the bromination and one after, your starting material absolutely must have 2 hydrogen atoms attached to the nitrogen. Primary amides have exactly 2 protons, so the reaction proceeds perfectly. But secondary amides, they only have 1 proton on the nitrogen. Once that single proton is plucked off and replaced by bromine, the molecule just hits a total roadblock. There's no second proton for the base to grab. The unstable anion can't form, and that beautiful 1-2 shift never even happens. So the Hofmann rearrangement is strictly an exclusive club for primary amides. Section 5. Perfect stereochemical retention, keeping the original geometry intact. This is a really crucial point for understanding this reaction. It occurs with perfect stereochemical retention. Basically, if your migrating group is chiral, it migrates with its 3D configuration completely unchanged, like 0 racemization. Why? Well, because that concerted shift we talked about is strictly an intramolecular process. The migrating group never actually breaks free and floats off into the solution. It just sort of slides over from the carbon to the adjacent nitrogen in one fluid motion. If it detached and became a free carbocation, it would totally lose its specific 3D geometry.
But since it stays tethered to the molecule the whole time, its original stereochemistry is flawlessly preserved in the final amine.
Section 6. Real-world industrial applications, moving from the whiteboard to the factory.
Okay, let's zoom back out. This is not just some elegant theory drawn on a whiteboard. It's a real, heavy-lifting tool in chemical synthesis. The Hofmann rearrangement is widely used to synthesize key pharmaceutical compounds, where you explicitly need a one-carbon shortening, for instance, converting nicotinamide into beta-aminopyridine. It's also super useful for creating specific amino acids. But one of its biggest claims to fame is the production of methyl anthranilate. That's a crucial compound used in everything from flavorings and perfumes to agricultural chemicals and even the artificial sweetener saccharin. In fact, there are massive, continuous production industrial operations that use this exact rearrangement on a starting material called phthalimide to reliably pump out methyl anthranilate and other anthranoic acid derivatives. By optimizing the molar ratios of the reactants in a continuous flow system, these modern setups are hitting yields over 80% and purities near 99%. That is seriously impressive for scale-up chemistry. But to actually pull this off at an industrial scale, you have to make some tweaks. Pure bromine gas is just incredibly dangerous and corrosive. So instead, factories often use sodium hypochlorite, which is basically industrial bleach, as a much safer, cheaper halogen source to kick off the rearrangement. They also use methanol as both the solvent and a reactant. By carefully balancing these reagents and strictly controlling the temperature, because if it gets too hot, your isocyanate intermediate degrades, industrial chemists can dramatically optimize the yield and safely scale this up for the global supply chain. And honestly, that brings up a fascinating point about the solvent, which I'll leave you with as a final provocative thought. Throughout this whole explainer, we said water attacks the isocyanate to form carbamic acid, which then loses CO2, right? But what happens if you swap out the water for an alcohol, like methanol, during the rearrangement? Well, because the isocyanate is highly electrophilic, if methanol attacks it instead of water, the reaction actually stops at a completely stable compound called a methyl carbamate. You don't get the amine right away, and you don't lose the carbon dioxide. Just by modifying the solvent, you open up an entirely new world of synthetic possibilities to explore. Thanks for joining me on this deep dive in today's explainer. Keep questioning those mechanisms, and we'll see you next time.